Good afternoon, everybody. My name is Andy Hock. Thank you, Kentaro-san and Riken, for hosting my talk. It's an honor to be here. As Kentaro-san said, I'm the Director of Product at Cerebras Systems. Cerebras is a startup company in California, in Silicon Valley. We're building a new class of computer processor and computer system to accelerate artificial intelligence computing in the data center. So I'll start with something that I think this audience appreciates, which is that AI has massive potential, but it could do much more with supercompute-scale resources. Today, we often see, as we just heard in our last talk, that AI can be used for things like remote sensing, but we require massive amounts of data with high-quality labels and massive computational resources just to experiment to try to find the right model to represent the real world. So with more compute, we could do more. And so I make the assertion here that AI has massive potential, but it's compute limited today. So let me say a little bit more about that. So first of all, AI has massive potential. We heard about this yesterday from quantum physics to quantitative trading, or from advertising and identifying cat videos to autonomous vehicles, commercial applications to civil applications like health and solving cancer, manufacturing to applications that are traditional in the HPC world like modeling and simulation. AI has awesome potential for all of these things to change the way that we work and live for Society 5.0 and beyond. But here's the problem. As researchers continue to make more and more progress with deeper, more computationally intensive models and larger data sets, what that means is that compute time goes up. So it's not uncommon for large models to take days or weeks, or sometimes even longer of compute time to run a single training experiment, right? To train a single model to convergence. Not only is that expensive on a large-scale cluster like K or Fugaku or places like Google or at a large academic institution, not only is it expensive, but that time it takes to train a large model constrains researchers' ability to experiment and innovate. And in the commercial world, it means it takes us a long time to do product development and get the best new applications to market quickly. So to get from days or weeks or even months down to seconds or minutes, we don't just need 2x or 5x or 10x more compute, we need hundreds of x or 1,000x more compute. And unfortunately, the challenge is growing. I'll say a little bit more about that in the panel. So I make the assertion here that we need a new compute solution to address this challenge. Most of the processors that are used in the data center today are general purpose machines, and they were fundamentally designed for other work. They are suitable machines for this work, but they are not optimal. One approach to shrink training time for large models today is to scale out a training workload over many small processors using data parallel scaling. This is one approach, but the engineering and the infrastructure costs are high, and the resultant model implementation that's scaled out over potentially hundreds or thousands of nodes is brittle to changes in hyperparameters or data set or network architecture. We often have to re-engineer a scaled out implementation if we change fundamentals of the model. So in a sense, scaling out a model to do data parallel training is a band-aid to allow us to use today's general purpose processors for a different kind of work, deep learning. So the performance gain that we need, this orders of magnitude gain, hundreds to thousands of x, motivated us at Cerebras to consider a new kind of architecture. And so this is where we come in. This is a picture of our office. We started in 2016, And we now have over 200 employees. As with most good computer hardware projects, we are now mostly software engineers. So about 2/3 software engineers, because when you build a new piece of hardware, you need to invest incredible resources in making that piece of hardware easy to use and easy to program with today's frameworks. So we think a lot about what is the right solution for artificial intelligence compute. Not only does AI compute require vast computational resources, right? Billions of parameters for typical models, and anywhere from millions to potentially trillions of samples to train a model for a single epoch. Right? So we're already talking about peta scale compute for large models. So not only do we need massive compute, but it needs to be compute that's designed for this work. So the fundamentals of neural network compute are sparse linear algebra operations. So we need many cores optimized for those tensor operations that are fundamental to neural network compute. So we need a lot of compute, right? That's number one. But not only is deep learning a computational challenge, it's also a challenge of communication and memory bandwidth. It is a problem of data in motion, where data flows into a computational graph, and the results are broadcast with a high degree of fan out and fan in between neurons in subsequent layers of the network, often with skip connections or residual connections, complicated communication topology throughout the network architecture. So not only is it a compute problem, but it's also a problem of data movement. So we need massive compute, memory, tightly coupled to compute, and high communication bandwidth. And last but not least, if we're going to build a new computer system, we better make it easy to program with the tools that users are employing today. So with all of those factors in mind, we built what we call the Wafer-Scale engine. This is a real chip here. It is the world's largest computer chip. It's approximately 215 by 215 millimeters on its side. It's the largest square we could cut out of the largest circular wafer of silicon we can get. It has 400,000 cores, all optimized for the sparse linear algebra operations of deep learning. They are all connected to one another over a 2D interconnect mesh over silicon, right? So in order to tie all these processors together, we're not going out over a PCIe board, over copper, over fiber lines. All cores can communicate directly to the other cores on this chip, directly over silicon. So we have incredible interconnect bandwidth. And each core has its own local bank of SRAM. So we have all on-chip SRAM, order 10,000 times the memory bandwidth possible on a modern GPU. And a little bit more. So each one of these 400,000 cores is a fully programmable compute core. Compute at the core level is triggered by data flow. So each core has a data flow trigger here and an adjacent fabric switch. Instruction set architecture, we have a full library of flexible general ops for control processing, things like arithmetic operations, load store, branch, as well as a set of optimized tensor operations to treat tensors as first-class citizens in the neural network compute. And this data flow architecture allows us to handle sparsity common in neural network compute with a high degree of efficiency and performance. So if a non-zero value comes in, the core will execute typically a multiply accumulate operation. But if there is a zero data value that comes into the core, we skip that and move on to the next non-zero value. So while a dense engine will multiply by zero, performing operations and wasting cycles and wasting power that doesn't drive your model towards conversion, our system will take that zero value and pass by it and only do useful, non-zero work that drives your model towards convergence. This is, in one way of thinking, this is an example of co-design at the system level, where we developed everything from the core architecture of our processor all the way up to the system level with the deep learning workload in mind. Another important factor of our chip design is memory. So in a traditional system, memory here in blue is separated from compute cores in a traditional von Neumann architecture. This is useful for a lot of work that is common today, but it's not great for deep learning where high memory bandwidth is required. So in a traditional memory architecture, we get shared memory, slow and over a relatively narrow bandwidth link out to off-chip DRAM. One thing that you can do to help drive up utilization with this kind of architecture is use large batches. So you communicate only once and then compute for multiple batches. But it forces you as a researcher to use large batches if you want to drive up utilization. And it also drives you to computing, training, or inference on a model in a sequential or serial sense, right? One layer at a time with a large batch of data. Instead, we took an approach of having all on-chip memory fully distributed across the chip. So each core in our chip has 48 kilobytes of local SRAM. And then in aggregate, there's 18 gigabytes of on-chip SRAM on the chip. This means that all the memory is fully distributed along with the compute data paths. And the data path at the core level has full performance from memory and can access its local memory in a single clock cycle. This also allows us to achieve full utilization with this device down to batch size 1. So we can employ large batches if you want to, but we can also allow you to run down to batch size 1 full utilization. So coming back at the chip level, the way I like to think of this chip is a cluster scale compute resource on a single piece of silicon. In addition to the cores and the memory, we have a configurable high bandwidth 2D interconnect mesh. What this allows us to do, instead of processing every layer sequentially in a model, allows us to take every layer of your model, illustrated here with these colored boxes, and compile and compute every layer of your model simultaneously. So this allows us to achieve model parallelism, model parallel scaling on a single chip. Gives us cluster scale compute performance with the programmability and programming ease of a single node. Right? So you don't need to think about how to scale out over many, many machines. If you want to, you can tie more than one of these chips together, but with 400,000 cores, you can do a lot in a single node. And also allows you to achieve full utilization down to batch size 1. So now that I've talked a little bit about the chip, I think the main question that would be in my mind is, okay, how do I program this? So we developed a software platform whose primary task is to translate the neural network model that you as a user express in a common Python-based open source machine learning framework like TensorFlow or PyTorch, and translate that computational graph into an executable that is compiled down onto our chip. There's a few steps in this. I won't go into too much detail here, but I'm happy to talk afterwards. Step number 1 is we take the compute graph representation from the framework, we extract that using our software, and we translate the compute graph into an intermediate representation that is the top of our software stack. That intermediate representation tells us about the compute requirements at each layer of the network and also the communication pattern between layers in the network. We then match high-performance kernels from our software library. And for us, a kernel is a common deep learning op like convolution for a computer vision network or LSTM or attention for a language, natural language processing model. So we match a kernel from our software library to each one of the layers in this computational graph. Those kernels tell us the compute requirements, the memory requirements, and the communication pattern for every single layer in the network. And we then allocate compute resources and memory resources to spatial areas of the chip. So this is how we map n layers from your neural network compute graph into n regions on our big chip. And that allocation of compute and memory and the routing configuration for data communication between those layers constitutes an execution plan that we bind as an executable and we ship down to the Wafer-Scale processor in our system. So at the end of the day, we take a program written in TensorFlow, we compile it as an executable onto our chip. We have this high-performance library of deep learning operations. And I think the last thing I should mention is that this is really a 400,000 core sparse linear algebra accelerator. And so we also provide a set of APIs that allow users like you to write your own kernels, whether those are additional deep learning ops that you need for your AI application, or if there are custom operations for HPC workloads like modeling and simulation or partial differential equation solving or signal processing. So this stack is customizable, allowing you to extend the system for other applications beyond deep learning. Okay, so that's the software, but obviously we couldn't package this big chip in a standard PCIe board. So we needed to think about the whole system. So this is the Cerebras CS-1. We don't have any marketing people, so our naming conventions are pretty clever. It's our first system, so we called it the CS-1. This is the world's most powerful single AI computer system. It has one big wafer-scale chip on the inside. It's programmable by that software stack that I just described, and it's made to be easy to install and deploy into a standard data center. It's 15 RU standard rack compliant server, so it's about this big, maybe the size of a refrigerator in your hotel room. It takes 20 kilowatts of power, right? Small fraction of Fugaku. But obviously, in addition to feeding this system power, we also need to feed it data. So we take in 1.2 terabits per second I/O over 12 by 100 standard gigabit Ethernet links. So even though this machine has this giant chip on the inside, we wanted to make it easy to install into a standard rack, give it standard 100 gigabit Ethernet connection to the outside world, and power it with standard cables. And although 20 kilowatts sounds like a lot of power, it's actually no more power dense than 15 standard 1U CPU servers. So I will say this, many of the challenges that we thought that we would run into building the big chip turned out to be relatively easy to solve, and some of the hardest challenges that we faced were in designing the packaging and the power and the cooling and the data delivery onto that big chip to keep it fed with data and power and cool. And that's our systems design challenge. So this is another example of co-design at Cerebras, not just thinking about the computational workload and the chip, but also thinking about the chip in the context of the whole system. So let's take a peek under the hood. I have a cool X-ray 3D view of the system. So this is the CS-1. The big chip that I held up is mounted here in the back upper left quadrant. It's actually mounted vertically into the system. We then have power supplies here. Our I/O system is here, the 12 by 100 gigabit Ethernet. So we're taking in power and data. All of the computation happens here. So this is also where we need to dissipate about 15 to 17 kilowatts of that total 20 kilowatt power over an 8.5 by 8.5 inch square. So everything else in the rest of this chassis is cooling. We have a closed loop internal water cooling system. So these are two pumps here. They pump cold water across the back of the machine. It's distributed by a manifold across a cold plate that's flush mounted to the back of the chip. That water then picks up heat, and we pump the water down into the bottom half of the chassis, where there's a large air-water heat exchanger. And we have 4 fans that pull cold air from your cold aisle, push it through the heat exchanger, and exhaust warm air out the back. And the cold water is then recirculated up and back through the system. So the system edge is an air-cooled system, but inside we have a closed loop of water. Okay, just a few concluding remarks. Thank you. So I'm happy to have this opportunity to tell you about the new system that we've built at Cerebras to accelerate deep learning in the data center. I hope we have an opportunity to work together, because this kind of machine gives researchers an opportunity to scale up their work from many small machines to one large one. And I think there's also an opportunity for machines like this that are specialized high-performance accelerators to live inside a high-performance computing cluster at a supercomputer facility. This machine has been built from the ground up to accelerate artificial intelligence and HPC workloads. I should say that the chip is real, the software is real, and the system is real, and it's running. It took us 4 years to be able to say that, but now it's true. The picture you see on the right is actually a real system that is deployed, installed, running at Argonne National Labs, a U.S. Department of Energy facility. And researchers there are using this system all the way from TensorFlow to accelerate deep learning research in health and science. We're looking forward to deploying more systems soon. My last comment is just a call to action. If you or your teams have large problems and you're feeling constrained by compute today, please come and talk to me. We're very excited to build collaborations in this space and to start thinking about future co-design programs. The system, the CS-1, is available commercially this year, but we're also developing partnerships and thinking about future systems and strategies. I'm looking forward to the opportunity to work together. Thank you very much.